welcome to Tech Talk. I'm Jeff Stipes, Chairman of Manufacturing Technology here at Muskegon Community College. My guest today is Jerry Nyland. Jerry is the Supervisor of Maintenance for all college facilities here. What we're going to look at today is the issue of energy efficiency. But before that, I kind of would like to take a look at the three major issues, or just review the three major issues that are here. We have renewable energy issues, we have alternative energy issues, and then of course what our topic today will be is energy efficiency. As you look at renewable energy, what you're constantly seeing anymore is the whole issue of wind and solar. And of course here in Michigan, particularly along the lake, wind is a hot issue because we're a good wind zone. You know, that's not to say you should or shouldn't do it, but you have to look at the area where you have that. So wind turbines are big in this area because of the wind capability. Solar is also very viable. Sometimes I think we're fooled here along the lake because of our winter cloud cover, thinking that we don't have good solar. But if you take a look at local companies, Padnos, Metal in Holland, Torsen Marine here in Muskegon, big solar systems. In reality, Michigan has about the same amount of hours of sunlight that Germany has, and Germany is one of the biggest users of photovoltaic or solar systems. Mm-hmm. Also in the renewable area is the biofuels. You know, the development and utilization of ethanol, biodiesel, and methane. The college has two new certificate programs currently available to students, one in wind and solar. And the wind and solar program is a focus on industrial and light commercial, not the big stuff. We'll probably get to the big stuff down the road, but this is the stuff that you're going to see now. You go to the local Meyer store and you see 6 turbines on the Norton Meyer store, you see one on the Fruenthal, or you see ads in the paper where they're putting them in. As well as the solar systems. And what we'll do is we'll teach students how to install and maintain these systems, and it'll be a hands-on. Every student who comes through our certificate program on that will actually have installed a complete system. In terms of the biofuels, this is a lot of chemistry and biology, and we have a certificate program for that for students who want to get into technicians. These systems, you don't just make methane and not monitor it. You have to keep a close eye on that. And just recently, the federal government has approved both these programs for student aid, for financial aid. So, they're up and ready to go and in the works. And then the third piece of that, what we want to talk about today, is this issue of energy efficiency. We're going to look at it from the standpoint of large facility, not from a home issue. Though a lot of the things we'll talk about here may be appropriate to house. But we're looking at it from there. And I guess the thing I would like to start with is what the people in the business call the low-hanging fruit. Okay. As I understand it, that's predominantly lighting. According to the data, lighting, your lighting represents about a little over a third of all U.S. electrical use. And it may not be the best bang for your buck, but it's easier to get at and change. And maybe you could tell us, Jerry, what are we doing in respect to the lighting issues here? I know you've got some things going on.
Well, we have a very large project going on right now, and it's going to cover over 3,000 fixtures on campus and over 9,000 light bulbs, individual light bulbs. Part of this is that we're converting what they used to call a magnetic ballast to electronic ballast. That's the fixture part of it. And you combine that with lower wattage light bulbs, we're going to be cutting the power consumption by those lights by virtually 1/2. Additionally to that, the project started out with using 34-watt bulbs. The college has opted to pay extra money and to switch to a 28-watt bulb in the bulk of our fixtures. It doesn't sound like a lot, but that little change of 6 watts per bulb will save the college $400 to $500 a month on the electrical bill.
Really?
And additionally, with changing out these lights and ballasts, we will be lowering our AC costs. You'll see in the classrooms in the past, we might have 3 or 4 colors of lights in there, which seemed a little odd. That's going to be standardized, and the classroom should be brighter, and the light color should be closer to natural sunlight. So there's many advantages to the light conversion.
Okay, now light is measured in lumens?
It's measured in lumens, and
I just put you on the spot. Not a problem.
What? Okay.
Well, we're actually going to have more usable light, better light for the student.
Yes.
In terms of that, and the consistency. Now,
Yeah, there's also two colors. There's a coloring rendering index.
it's a fluorescent issue, right?
Correct.
Okay.
Well, all lights have color. It's based on a Kelvin scale. The higher the number, the closer to sunlight it is. And then there's also a coloring rendering index number, which basically the higher that number is, the cleaner the light is.
Oh, really?
So we're switching to a cleaner light and closer to sunlight.
Okay. Now will this, I know we're looking at energy efficiency, but just out of curiosity, will this make it easier to read a computer monitor if you're, say, in the lab down in the information commons over in the Meyer?
In some areas it will.
Okay.
In the older parts of the campus where our lighting levels were a little low, it'll improve that. It's not going to help with the library or the higher ed center in the newer areas.
Now, what do you, and I don't want to put you on the spot, but what do you anticipate the payback or the break even on a project like this would be? I mean, does it pay for itself in 2 years, 5 years, 10 years?
Well, the lighting portion of the project is probably 6 to 7 years.
Okay.
We have some areas, our maintenance building, gymnasium, those are closer to a 3-year payback. They use a different type of light fixture.
Okay.
And the power savings are quite a bit higher in those locations.
Okay, so when you're talking 6 to 7 years, you're talking about an average campus-wide, but within individual areas of the campus, it could be as little as a 3-year payback on it. Okay, so you're looking. Okay, so that's important to understand. Now, I know we use a lot of what we use is the fluorescent around here, but we've got this issue coming up in 2012 where the incandescent bulb starts to go away, and we bring in, what do they call it, the CFL, the compact fluorescent.
Compacts, yes.
And I know you've played around with some LED lighting over in the theater. Can you tell me a little bit about that?
The LED, well, we're looking at LED, and we're also looking at magnetic induction lights.
Okay, now that you're going to have to explain that.
Yeah, okay. The LED is basically an electronic light fixture. It has a circuit board on it. It's a light emitting diode. They've made tremendous progress with those in the last few years. Initially, the problem was getting white light on them. It always had kind of a blue tint.
Yeah, okay. I've seen that.
That's been conquered. The second thing is heat. The LED lights generate a lot of heat, and I have a little trouble grasping that because the power consumption is way down. I don't understand the heat generation, but it occurs.
The LED generates heat?
Yes. The LED bulbs and fixtures generate quite a bit of heat. So they have to put a lot of heat sink or heat dissipating metal into the fixture to dissipate that heat. Because in the summer, an outdoor LED light, if you can't get rid of that heat, you're going to cook it. But they made tremendous progress there, and it's at the point now that the costs are coming down that they're worth looking at. We have several screw-in floods on campus that we've been testing for 2 years. I have an LED parking lot light out by the satellite dish complex that we're testing, and we will be installing 2 more in the front parking lot that we'll test over the next year. Now, power consumption on those fixtures will drop from about 340, 350 watts per fixture to about 100.
Well,
so that's tremendous.
60+%.
Mm-hmm. So even though the fixtures are rather expensive, we have almost 200 of those fixtures on campus that light the parking lots, and they burn anywhere from 10 hours a day to half of them burn from sunset to sunrise. So they're big power use.
Sure. Now,
items.
Is their life longer, and do they last longer?
Well, LED, the fixtures we use now have a 3 to 5 year life. They're projecting the LED to run 8 to 10. And then the magnetic induction, they're projecting that that'll be 100,000 hours.
Really?
I'm looking at a test on those too, but that requires a head change. It's a little more difficult than the LED conversion, and the cost isn't quite down there. But 100,000 hour light would last for 10 years.
Wow. Okay.
Right now we have to change them about every 3. So those maintenance costs also are added in there. We don't have to rent the list. We don't have to pay the labor. We don't have to worry about bulbs going out.
So the issue is not just energy savings, it's maintenance dollar savings as well, and longevity of the...
Longevity, light quality is also an issue.
Light quality.
The bulk of our lights now are metal halides in the parking lots. They lose about 10% output the first 3 years. So when you're 3 years out, you're at about 70 or 75% of your original lighting output. And you have to relamp to get that back up. An LED or a magnetic induction does not lose lighting output over the life of the fixture. So it also gives you full lighting level for years.
Good.
So a much better product.
Excellent. I want to switch to something I know that's a big issue for you, and I know it's going to be a big issue for the college because it's not what you would call low-hanging fruit, but it's from an energy savings, it's the air handling. And I think a lot of people just don't understand the concept of air handling within a facility. Maybe you could explain just briefly what do we mean by air handling, and then what are we doing that's going to generate some real energy efficiency savings in respect to air handling?
Well, with HVAC systems, there's a number of
HVAC.
heating, air, ventilation.
Okay.
HVAC.
Yeah,
Heating, ventilation, air conditioning. Yeah.
Okay.
There's a number of ways to do a facility like this. When MCC was constructed, they built it with what they called a constant volume system. A constant volume system was designed to supply a certain airflow to an office. For instance, if it needed 100 CFM,
Cubic feet per minute.
Cubic feet per minute, you would get that no matter what, anytime the unit was on.
So it's constant.
Constant.
When the unit's on, you've always got that 100 cubic feet per minute.
Correct.
Whether
So,
anybody's there or not.
Whether they're there or not. And the other thing is if it's calling for heating, with a constant volume system, you have two dampers. One for the heating duct and one for the cooling duct. So if you call for a little bit of heat, it opens the heating duct up a little bit further and closes the cooling duct a little bit. But they both remain open at all times a certain percentage. Okay. So basically you're throwing heated air and cooled air into that office all the time.
Okay.
Okay. So it's a very comfortable system, but it's an energy hog. A more modern system, and what we're converting now to, is what they call veritable air volume.
Now, not variable, but veritable.
Veritable air volume.
That's all. Yeah, I know I've misspoke on that a number of times,
Yeah.
but it is veritable.
Veritable air volume. And the concept there, you separate the heating and cooling systems. The dampers work independently. So if the thermostat is satisfied, both the heating damper and the cooling damper will be down to a minimum airflow. So instead of that 100 CFM that you were putting into the room, you might be putting 10 CFM. And then when you call for a little bit of cooling, it might go up to 20 or 30 or up to the 100.
Okay.
And then as it becomes satisfied, that cooling damper will close back down, and if it calls for heat, the heating damper will open up. So the great advantage is that you're not putting conditioned air, both heated and cooled air, into the room constantly. And how they get to that point now is by using freak drives and static air sensors on the main air handlers. So what they can do is actually vary the speed of the blowers to produce only the cubic feet per minute that the entire system needs, instead of putting this massive amount into the ductwork and into the rooms. And then, since you couldn't use all of that treated air, you usually exhausted it outside.
Okay. All right.
We can now recirculate that air, reuse it, and only bring in the minimum requirement for ventilation to give us fresh air.
Savings-wise? I mean, I know this is an expensive project, but what's it?
It's an expensive project, but we're projecting that this will save the college around $2,000 a month.
Okay.
In the electric and gas and AC bills combined.
Now, what's the projected payback on something like this for a facility? I mean, got to remember, we're talking about large facilities today. We're not talking about your home. But in a large facility like the college, what do you anticipate your payback will be?
This part of the project, we're looking at an 18 to 24 month payback.
Well, that's
which is phenomenal.
That is.
And we're using that to help finance some of those longer payback items, like some of the lighting.
Well, just good planning. So you're using the short-term stuff to finance the long-term.
It's an excellent project.
Wow, that works really well. This sounds very exciting. I know that, like your air handling system, you're talking about controls, and I understand there's a lot of electronics controls in this thing, and we probably should talk about energy management systems.
Okay.
For a homeowner, an energy management system might be a programmable thermostat.
Right.
That's the base concept. But in a facility like this, That's not even close to what it is,
No,
right?
no. We have close to 500 pieces of heating and cooling equipment on campus. So we can't run around and change the thermostat up and down every time we need to heat, every time we need to change the temperature in a room. Years ago, again, when the college was built, it was all a pneumatic system, which is basically an air-driven system.
Okay.
And as part of this project that we're working on now, we will be close to 90% DDC controlled or digital controlled.
Digital control, okay.
Okay. There's a number of advantages to digital control. Probably the number one thing is that we can pull up any air handler, any room at my desk or any one of my technicians' desks and see what's going on, change the thermostat set point, look at the air flows, diagnose problems, and receive alarms when there is an issue of any kind. So that saves tremendously on our labor costs, plus no one can cheat.
Okay.
Pneumatic thermostat was very easy for somebody to pop the cover and dial it up or dial
yeah,
it down.
Some of us are guilty of
Yeah.
making those adjustments.
And we've taken that away from you. It cannot be changed in the room. If you tamper with that thermostat, the thing's going to shut down.
Okay. Well, it's interesting, and you know, having this system, and we'll talk a little bit more about it, but it's also I'm realizing as department chair, there's a learning curve for faculty on this. I know, watching the system over the last few semesters, you know, if I've got a class in room 502, I know you keep the room at what I would call a maintenance level, whether heat or, you know, based on, but I noticed that the system seems to come on anywhere from 20 to 30 minutes prior to the start of class and brings it up to the temperature we want for the class, and then I noticed that usually about 15 minutes before the class is over, it shuts itself back down and it comes back to the maintenance level. And I know we've had some faculty who have you know, made some room changes and not notified central scheduling, and this all comes out of central scheduling. So if I, for whatever reason, pop into a different room that I'm scheduled to be in, that's going to be in a maintenance level, and
you could be in a sauna.
I could, yeah, exactly,
yes,
yeah. So now, is this a PC-based system? Does it run on a
well, it's actually beyond that. It's web-based.
Oh, really?
Now,
so you could control it from off-site?
I can control it from anywhere around the world.
No kidding.
I've gotten numerous calls on weekends and at night. You know, just like you said, somebody's using a room that we didn't know was supposed to be scheduled on. I can turn that room on. I can bring on major pieces of equipment. I can do diagnostic and some service remotely. If I have a unit that's not quite putting out the air conditioning that we need, I can boost its output from my home.
Okay. So if we've got a problem, the potential you could at least correct the condition in the room until you can get somebody in from one of your techs in to solve
in many
the problem.
cases,
So you're not just there stuck in the water with a sauna situation, or.
And this is beyond just being able to control it. We have graphical screens that show all the major air conditioning components and how they interact. So we can pinpoint where the problem is in the unit, not just look at what the unit is putting out, but we can look at all the interior areas of the unit and pinpoint what section is giving us the problem. Wow, and that's how we can work around it.
That's huge. That is a real, just from a person in your position, just to be able to manage that in that way.
It is phenomenal.
Couple other things. We're starting to run out of time a little bit. I'd like to talk a little bit about the new green roof we put in over the what used to be the library, and when we abandoned the old library and built the new library and Hendricks Meyer Tech Center, then that old library area became administration. But it's got a roof. It's got a completely, and you've just recently put in a green roof. You know, what is a green roof? I mean,
what is a green roof? Well, we put in what they call a trace system. Came from Hortec, just down the road in Grand Haven.
Local provider.
Local provider.
Good.
Yep. And the material or the plant that we use, it's called sedum. It's grown for the geographical climate. So the sedum that was grown for our roof was designed for this area. Detroit might have a little different product than what we would have. Kentucky would have a different product.
Okay.
So the product is designed for this
But
area.
it's all sedum.
It's all
Just
sedum.
variations of
different
sedum
types,
based
right.
on localized.
And you get different colors, different types
Okay.
of flowering, and it changes throughout the year. You'll also notice on the roof garden there's a pattern that was installed. So it really is quite attractive,
Yeah,
particularly
okay.
from one floor up on the roof, looking down onto
Yeah.
it. There's a few things that it does for us. It reduces the cooling load because it acts like the plants in the soil absorb some of the sunlight that would normally directly impact our roof deck.
So your roof temperature is lower.
Our roof temperature is lower, so it
Okay.
saves on air
Now,
conditioning
I've heard
in
it can be
particular.
as lower as by as much as 30%.
I've heard that too. I've
Okay.
never.
No, we haven't proved
We
it,
haven't
but-
proved it, but
okay.
those are the numbers I've heard.
Okay.
It also reduces runoff into the storm system. And in this case, our storm system is going to 4 Mile Creek, so we're reducing the flow off from that roof deck into the stream. Of course, that is also reducing, like perhaps bird droppings and that type of thing, because actually the plants will use the fertilizer,
Okay.
the nutrients
Okay.
from the droppings rather than just having them go down the drain. So those are good things from it. Additionally, it protects the roof membrane. Solar sunlight rays attack roof membranes and break them down over time. Well, with the plant life and the decking material we have over the roof deck, it should extend the life of the roof membrane for years, perhaps 5 or 10 years. So that's also
All right, so you have
Good
you reduce the temperature, and if the roof is cooler, your energy demands are less.
what. Yes.
And if it can pick up that water, if through some evaporation, you can reduce your amount of runoff into whatever your storm sewer system is. But there's some prerequisites for these things, right? I mean, you can't put that on. You got to put it on a flat roof. Right?
Well,
obvious. That'd probably be the obvious
Well,
one.
the biggest problem is weight.
Okay. Okay.
Our system weighs anywhere from 30 to 35 pounds per square foot. I believe.
Okay.
Don't hold me to that
Yeah.
number. And that is pushing, on a lot of roof systems and on our main building, that would probably push us beyond the design load of the roof deck, and we'd end up with a roof garden inside the building. The roof collapsed.
Okay.
We were fortunate with the old library area or the new administration area that was designed to be built on top of, to extend upward. So they put a lot of strength into that roof. It's actually a concrete deck.
Okay.
The rest of the college has what we call a gypboard deck and couldn't handle the weight of a roof garden. So.
Now, can a roof section that was not designed to that, can it be modified to hold it, or are you
Sure.
just pretty much dead in the
Yeah,
water?
you could.
Okay.
As long as the main structural steel components could handle
The load.
the load
Okay.
and the additional support for the roof deck, you could do it.
Okay.
But it would require some engineering and some capital expense to get there.
Well, this is fascinating, and in every situation, not only does it reduce our energy usage and the old carbon footprint thing,
Exactly.
but it also helps us keep costs down to students, because the more money we can save, that gets passed on in
Exactly.
reductions into it.
And it's in a very attractive area now,
Oh,
too.
yeah.
Before it was
that's-
just a roof
yeah,
deck. Now
yeah.
it's gorgeous.
And that's open to the public, right? They can come
Exactly,
over
yeah.
and see it, and it's right next to the nature trail. Was it the Kelsey Hayes
Well-
Nature Trail? And that's there. So you could actually come over for an afternoon and tour the roof garden
Sure.
and take the nature trail and
Well,
make a nice
as
little-
you know, we've invited some Grand Valley people over to visit it. It's nice to show off because you don't have to go onto the roof
Yeah,
to see it. You
exactly.
can
Yeah,
walk-
at least at our level, you can walk right up to it. And there's a little
Exactly,
path that goes
yeah.
around it, and you can even have a picnic out there, right? There's
Sure.
a table. I've seen a lot of faculty and staff out there having
Mm-hmm.
lunch. I know we're not doing this yet, but I know I've heard you talk about it, and it's this daylight harvesting
Okay.
issue. And could you mention what is daylight harvesting?
Well, basically, we sense the sunlight level, or the light level that we're getting during the day, and we shut off lights in areas where we have a lot of light gain through the glass. The connector hallways would be a good example of an area where we can.
Okay,
where
we have a
can
lot of
save.
windows.
Yes. Yeah, any place that there's a lot of window.
Okay,
You can
outside
use,
wall predominantly if a classroom, okay.
and in the past, those systems were somewhat separated from our energy management systems. But we're looking at now tying them into the same DDC control system
That's your
that we're
digital
using
control,
for
your direct digital control.
that we're using for our HVAC and energy uses, and we'll be able to sense that solar or even tweak it at any one time if we decide that we've got an area that we can bring down.
Okay.
It's still rather expensive because you have to install relays where the electrical light power is supplied from, and then sensors on the roof and do the interconnection. But it also has great potential.
Well, but you do have, with the energy management system, you have a major piece of the infrastructure for that thing, right?
Oh yeah, we do.
Because it ties right into that system.
And you can look at another area that we looked at using it, for instance, the higher ed center.
Okay.
We have several, well, all 3 floors, we have several classrooms that face the sun, particularly in the summer.
I was in one of those, and it was hot.
It is.
And we wound up having to, marvelous daylight, but we had to shut all the blinds to.
Right.
try and
And
control
part of the
temperature.
problem you may have there is that you may need light, artificial light, where the instructor's at, in the back of the room, but you may not need it near the windows.
Okay.
So with this type of system, we could shut the lights off next to the windows and leave them on for the instructor.
Okay, so basically when you're talking daylight harvesting, you're simply saying if you have a situation where you have enough daylight or sunlight to warrant not having the lighting on, you're able to turn the lighting off. And then when it does, if it gets cloudy or overcast or night comes, you're able to put that lighting back on. So you're going to maintain the same lighting level, it's just you're going to use some of the natural light from the sun
Exactly.
to do it. Okay.
Exactly.
Interesting.
And one step beyond that, they even can tie in blinds or shades to this system
Oh, to open it, okay.
to open and close them automatically to vary the light to the room.
Wow. Well, we are just about out of time. I want to mention again today, my guest today, Jerry Nyland, is the maintenance supervisor for all the facilities here at the college. And we've been looking at the issue of energy efficiency. Things that we're doing here at the school that are going to not only reduce our energy utilization, but also enhance our carbon footprint. Again, Jerry, thank you
good.
so much. It's been a
Thanks,
pleasure.
Jeff.